All right. Hi. My name is Oliver Kennedy, and I'm a faculty member here at UB. So I've been working with Spark kind of indirectly for the past year or so. This represents kind of more of a hands-on approach to kind of interacting with it. So if things break down, I apologize. This will involve live demos, so buyer beware. But okay, before I get into talking about Spark itself, I want to give you a little bit of history. Way back when, in the early days, computers were used for tabulating data. At some point, Todd came along, proposed the relational model. A bunch of people picked this up and said, let's build some systems built around it. Postgres, System R, Oracle DB2 all came out of the 1970s. Then we had a couple of desktop databases, Lotus and DBase. 1990s rolled around. We started getting really fancy types of databases dealing with objects and object relational databases. And then 2000s rolled around and we hit kind of the dark age of databases. So kind of what happened, Google came along, wrote this paper called, two fellows from Google came along, wrote this paper called MapReduce, and it basically said something to the effect of databases suck. They don't scale, they don't work when you want to throw a ton of data at them, and so use this instead. Of course, they said use MapReduce, but they didn't actually give anyone any code. Of course, then Yahoo came along. They started giving out, they created their own MapReduce implementation called Hadoop, spread it around, made it open source, and for a very long time, this was pretty much all that anyone talking about big data looked at, MapReduce. So MapReduce did kind of scratch an itch that many people working with large data sets at the time had. In fact, it scratched several itches. So first off, it was to write MapReduce code, you basically used the same languages that you were familiar with. At this point, everyone was using Java. You write some Java code, and all of a sudden you get a lot of the nice properties of a database. It distributes it, takes your code, and it basically runs it across a whole bunch of machines, and you get a lot of that for free. It had a couple of metaphors, map and reduce specifically, that were extremely friendly to distributed computing. So the programmers, as long as they could write their code in a way that could be expressed using map and reduce, they basically got distribution for free. And it had a really, really battle-hardened, resilient runtime. Any computer working on a MapReduce task could break, and the system could still recover from it. And essentially, when you're working with thousands or tens of thousands of nodes, there's a good chance that something will break while things are running. Okay, so MapReduce, and in particular Hadoop, had some very nice properties. It also had some unpleasant properties. So those languages that were very nice for programmers were not particularly declarative. What I mean by that is you wrote this piece of code, and that piece of code got used once, or for one specific project, and never got used again. The database engine had no idea what was going on in this big block of code, and so the database engine couldn't reorganize the data to take advantage of things like indexes. MapReduce had some metaphors that were very easy to parallelize. Unfortunately, working with those metaphors people started stretching very much in order to get their code to work be able to express their ideas using map and reduce. And so this was painful. And while the runtime was incredibly resilient, it was also very slow. Hadoop takes a minute or so just to get running in the first place. So kind of the comparison here, Hadoop is your battle-hardened tank. Databases are nice, fast Ferraris. Granted, they don't scale out quite as much. They don't work with as large data, and they certainly, if a database breaks down, you're probably going to spend a while bringing it back up. But they were a lot faster. So along came a group out of Stanford called the AMP Lab. Sorry, not Stanford, UC Berkeley, called the AMP Lab. Mike Franklin and Joe Hellerstein. One of their students basically sat down and said, you know, I can re-implement MapReduce, only I can do it far better using all of the 4 decades of database research that MapReduce decided to ignore, and I can do it in my sleep. And so basically, rather than implementing a half-assed database, at least implemented a three-quarters-assed database. And it's called Spark, eventually got released under as part of the Apache incubator, and eventually turned into a full Apache project. So Spark has a couple of very nice benefits, many of which were also benefits of MapReduce. It works with a variety of different programming languages. In order to write a Spark query, or something that a database person would describe as a query, you simply write regular code. Built-in Python primitives, built-in Scala primitives, Java and R, and I think I might be missing a few languages here as well. You just write regular Scala, Python, Java, R code, and it magically works with Scala, with Spark, excuse me. So Spark provides a couple of additional metaphors, not just map, reduce, map and reduce. It provides a whole bunch of other tools that make it possible to do things that you would expect SQL to be able to do. And because it's Spark, it also is able to throw these queries at a huge distributed runtime and be able to compute the query results much more efficiently. And just like MapReduce, the metaphors are there to make it possible to parallelize your code, but there are a lot more of these metaphors, and they're a lot more friendly to use. And of course, all of this is intended to run on a very resilient cluster that can, if anything breaks in the process of execution, Spark can kind of fix things. Okay, so let me kind of give you, right now I've been kind of describing Spark more in the abstract. What can you do with Spark? What is Spark exactly? Well, Spark is essentially a way of interacting with large chunks of data. And those data can be, as a simple example, you can take a text file, you can load it into Spark. And when you point Spark at a text file that could be sitting in HDFS, it could be sitting on your hard drive, you point Spark at a text file, it gives you one of these objects, and I'll explain what I mean by this in a moment, but it gives you this object called an RDD. This RDD can be read out from a text file, can be read out from a whole bunch of other things. HDFS, relational database, can read out from JSON data, can read out from, basically if you have data, there's probably an adapter that will translate whatever data you have into an RDD. And once you have an RDD, you can start using it with Spark. Of course, RDDs, as I'll describe in a little bit, are kind of a very low-level method for interacting with your data. So on top of this, the Spark folks built a tool called data frames. If you're familiar with R, with pandas, it is literally the same thing. Data frame is very much like a SQL table. And then on top of this, you can either write code using your favorite language that directly interacts with the data frame, or you can write code using SQL. You can, they have a couple of other tools, like for example SparkML, that can read in from a data frame. And essentially they're kind of building this entire ecosystem that can interact with data frames, and these data frames and RDBs are kind of a way of multiplexing access between a variety of different ways of interacting with your data and a variety of different forms of data that you begin with. Questions so far?
How big is big? You talk about big. The databases are things like, you know, the phone company. Need a lot of data. Yeah.
So
that question was coming.
the input to Spark can be any existing database table or any files that live in Hadoop. So I don't have exact numbers for you. I can look these up, but I mean Hadoop is designed for dealing with gigabytes or even terabytes of data. And
That's rough.
anything that you can do with Hadoop, Spark will do it faster. That's basically the gimmick. Anything you can do with Hadoop, Spark will do it faster, and in a more friendly programming environment. Does that address your question?
Quite so. Thank you.
So Spark adds a bunch of additional metaphors. Does it add any colorful metaphors?
Okay, so since Spark is built on them, and since data frames kind of extend the idea, I'm going to spend a little time briefly talking about RDBs. I'll then describe how data frames extend them, and then I'll get into the actual meat, talking about, we'll do a couple of quick examples with Spark. Okay, so RDDs, or resilient distributed data structures, are essentially like a list, a Python collection, list, dictionary, what have you. You can think of them like a Python list, like a JavaScript array, like a Scala collection, like a Java list. Go down the list of these, but it's essentially a bunch of rows of data with a couple of caveats. So first off, it's read-only. So unlike a classical database table, you can't insert, you can't update, you can't modify. You can only read, you can only run select statements on the table. But that said, you can create new RDDs, and the way that this is implemented, this is really inexpensive to do. You can create new RDDs by modifying existing RDDs. So for example, you could say, give me, take this table and take this other table, union them together, and then that new thing is an RDD as well. And as far as Spark is concerned, an RDD is just a collection of these rows. Spark has no idea how to interpret the rows. It doesn't try to do anything with them. It just knows that there is a list of things, and it's up to the programmer to keep track of what those things are and make sure that they're accessing the rows correctly. RDDs are also evaluated lazily. What I mean by this is that as you transform an RDD, and this is why transforming them is cheap, as you transform an RDD, Spark doesn't actually run the queries then and there. it saves the queries that you've been running, and until you actually access the data, it doesn't do anything with it. You can think of the transformations as building views in a database. As you write more and more code, you build a more and more complex view, and then as soon as you actually want to access the content of the view, that's when Spark goes out, sends the query to the cluster or to your local machine, and actually runs it. And then, of course, as soon as it does construct this, Spark takes care of all of the messy work of actually figuring out which computers, which workers are available, contacting each of them, creating a jar file with all of your code in it, sending the jar file, sending the serialized objects. It takes care of all of the messiness of getting your data, getting your code to the workers, and actually making sure that they run. And it does this in a resilient way. If anything fails in the process, it recovers, restarts the computation, or restarts at least the necessary parts of the computation. Questions?
Yeah, so
Yeah.
does Spark, so is Spark is only for select queries and not for updation? Because you said it's only read-only, so I want to know, like, in general, is Spark is only for select queries or even for updation or insertion and do for that as well?
So Spark is, like Hadoop, a read-only database. You can ask questions of it, and you can build new objects or build new tables. But the assumption is that all of the data is fixed. And this is, it relies on this to make it fast, to make it, Spark relies on the fact that everything is read-only to make sure that everything stays stable. If something breaks, because it keeps track of how the result was constructed, it knows that that result can never change, so it, if anything breaks, it can just reconstruct the object from its component parts, or the RDD from its component parts.
Well, but in case of transformation, in a relational database, it's easier to transform it. But when we have data in Spark or Hadoop, what do we do in case of transformations? We can't use an insertion, then it's only for select queries.
So when I say transformations, you can think of a table as being, even in a regular database, you can think of a table as being versioned. If I insert a new row into the table, that could be expressed in a read-only way by saying, take the original version of the table and union it with the row, a table containing the one row that I want to insert. And that gives me a new version of the table that behaves as if I inserted a value into it. So Spark lets you think of tables that way. You can union new rows into the table. You can filter rows out to simulate deletions, and you can transform records. You can create a new table that is kind of like select where you rewrite the contents of the table, but as far as Spark is concerned, that is a new object, a new RDD, and the original one stays unchanged. And if any other piece of code has a pointer to that original RDD, then that doesn't get updated. Does that address your question?
So we are just saying that you build a new, like a view table, and then you make transformations on that, right?
Yeah. So you keep, essentially you keep building views in Spark. You can simulate insertions and deletions by doing this, but you can't actually
Modify the original data.
Once you have a pointer to an RDD, that RDD is fixed. That represents that you can't change it.
So when you start to stack these things on top of each other, do they become very space inefficient? And, I mean, obviously there's not a performance cost to actually accessing them, but
Well,
it seems like you could end up building a whole lot of things that are effectively duplications of one another.
Yes. I mean, the main use case for Spark is analytics, OLAP style workloads. So you're not really, you can simulate these types of transformations, but that's not really what Spark is aiming for. So yes, there would be some space inefficiency, there'd be some performance inefficiency, because you still need to, every time you access the object, you need to transform all of the objects that went into it. Spark will do some intelligent caching along the way, and you can give it some hints about what it should be caching. Yeah, it's not really, Spark is not really aimed at workloads where you want to transform your data. Or sorry, Spark is not aimed at workloads where you want to modify your data. Yeah.
So you mean to say it's kind of a static data inside there?
Exactly.
And, it cannot be used for the transactional databases or something?
Yeah, so Spark is not meant to be used transactionally. Okay, so RDDs, Spark gives you a couple of different ways of constructing an RDD. So I said, what is an RDD, but where do they come from? So if you have any collection type, a list or an array in Python, a list or an array in Scala, a list or an array in Java, data frame in R, well, a list in R, Spark gives you a special parallelize function that magically turns it into an RDD. Basically says, here's a bunch of stuff, treat it as an RDD, and then as soon as you start running computations on that RDD, Spark will send it to the appropriate workers and compute things. You can tell Spark to load a text file either from your hard disk or from HDFS, in which case it will read in one code per line. You can load in database tables, or you can apply one of a variety of different functions to transform an existing RDD. Again, giving you a new RDD rather than modifying the existing RDD. I'll give you some examples of this when we start going through. So RDDs, if you're familiar with functional languages, RDDs basically give you flat map, map, and filter. Don't worry about that for now. Basically, the analog is select where the select clause, the where clause, and then something that lets you implement both. So, okay, RDDs have all these caveats. The one that people found incredibly difficult to work with is the fact that Spark doesn't actually try and interpret what's in the lists. People got used to databases where you had this very nice structured data. You had data with a schema. And so when I say data frames, a data frame is essentially an RDD that has a schema on top of it. It's enough to tell Spark how to interpret the data and gives you a collection of other tools that you can apply to transform the data in a way that is a little easier to understand. This kind of needs to be seen to appreciate it, so let me see if this will work. So, from the Spark website, you can download the Spark the latest Spark package. It comes wrapped with Hadoop. So this is basically a self-contained, all you need to run Spark into here. And when you open it, there's a whole bunch of stuff. One of the tools that comes with Spark is, okay, so I said that there's a bunch of different languages that you can use Spark with. The one that I'm going to use today is Python, since I don't want to spend an hour introducing Scala. The code that I'm using translates almost directly to other languages, and the Spark website has some great tutorials if you need to know exactly how those translations work. Mostly I want to give you a sense of what you can do with Spark. So there's a couple of ways of interacting with Spark, even if you know what language you're using. You can tell Spark to just run a Python file. So there's a couple of libraries in Python that let you interact with an existing Spark server. Or there's also a handy utility called PySpark, which gives you a Python interface that that essentially starts up all of the Spark infrastructure around it. So you can basically start telling Spark what to do immediately. So once you see the nice ASCII art, you can start running. You can start running code on Spark. So, like I said, you can read in data from a variety of different sources. One of these sources is just regular text files. So one of the text files in here is the README file. Nothing too fancy, just there's a typical markdown file. But let's say, well, everyone's favorite thing to do with Hadoop is word count. So let's try that. So we're back in PySpark. I want to first open the data file. So Spark gives me a couple of different functions that I can call to read in data depending on what type of data I have. So I want to be able to refer to this. So basically telling Spark, okay, I have this text file, it's sitting on my hard drive, I want you to read it. And sit there, Spark chews on it for a few seconds. It's still designed for really large data sets, so there's, it takes a few seconds to get warmed up, but the text file, this object that Spark has given me is a data frame. And the way to interpret this is it's a data frame with a single column called value that's a string. What is that string? Well, we can take a look. Can everyone see down at the bottom? I can move it up a little higher.
Question, in the example that you're giving us right now, are you connected to like some type of server or some type of Hadoop cluster or just?
It is connected to a server, but it is a single node server running on my machine at home.
Okay, so this is just shipped from just downloading Spark.
You download Spark, you run /bin PySpark, and you're in it.
Oh, great.
I will get to the cluster stage. Spark gives us for every data frame a function called show, and this is basically what I'd get by running, this is analogous to actually running the query and then displaying the results in a table. And you can see basically every row, every line of result, every row in the result has one column, value, and the value of that column is the content of each line of text. So this doesn't quite get us to word count, although we can do a few basic aggregates like tell me how many lines I have. So if I run text file back count, it tells me I have 103 lines of text. There's a few other basic things I can ask. So if I don't care about, if I just care about the first line of the result, there's a first method, which gives me back a row with the value that I'm looking at. And if I want to turn this into a Python array, I can also tell it, give me the next, let's say 10 records, give me the next 10 rows of data, and that's kind of like calling first, but instead of giving just the first value, it gives you the first however many, in this case 10, the first 10 values. Okay, so, all right, this is, we're looking at the text file, but we're not actually doing any sort of computation.
What if you can't remember the command that you want to run? Does it have any help for that?
Yes, there's very good documentation on the Spark website.
Okay, but there's not one built into the CLI. So like a text file.help or something like that.
It is entirely possible that that exists. Oops, sorry.
I can look. You can keep going.
As far as I know, no, but no autocomplete. Okay, so we're not actually doing any computation here. Let's actually do something that looks a little more like SQL. This is a database meetup after all. So for this, there's a library of functions that PySpark provides. Just going to import that library there. And now I can basically start querying my data. So let's say that I want to split out all of the words. One thing I can do is say text file dot select, and this is literally what you would get with a select statement in SQL. Let's say I'm interested in taking the value and creating an array of all of the words on each row. So one of those functions that I just brought in, split. And now I need to pass to this command a reference to the specific column that I'm interested in splitting. So this is slightly different in each language, but PySpark gives you this column function, or col, and the column I'm interested in is value. So this gives me a reference to the value column, and I want to split it on any white space, basic regular expression. So I run this, and it gives me a new column. It's able to figure out that the new column is of type array of string, and it decided to call the column based on the function that I gave it. So that's not particularly helpful. Luckily, Spark has something like select foo as var. It's called name. So let's call it words. So now this gives us a data frame. Oops. Putting as on the wrong how you know it's a live demo. So now we have a data frame, one column called words that is an array of strings, and we can save that for our own use. And you'll note that this has been fairly fast because we're not actually computing anything. All we're doing is telling Spark, okay, give me a new RDD or give me a new data frame that is the result of applying this split function to every row of the data that I got from my text file, which it now has cached. So file words, let's say. So now we have another data frame, filed by words, that we can refer to. Okay, another useful function to have.
Wow.
Yeah.
How can we look at that result?
Call show, and it gives you every row of the data. You can see it's called, the one column is called words, and everything is an array of all of the words that are on each line. So, is that right?
Thank you.
Mm-hmm. So another useful thing, now we have an array on each line, but we're interested in the individual words. We're doing word count after all. So we can, so PySpark gives us kind of a reverse aggregate operation called explode, which we want to take the words field and explode it. Let's call it word. And again, this gives us a data frame, but now instead of being an array of strings, it's just a string. You can see what that looks like. And by the way, show doesn't give you all of the table, it just gives you the first 20 rows, I think. But again, you can see now the very first word is there, the second word, the third word, that's the end of the first line. The next line was blank, so that just gets turned into a single character. And again, we've essentially taken the arrays and kind of rotated them, so now, put another way, we flattened them out. So instead of a one array per row, we just have one array entry per row. Yeah?
So is that order preserved? In other words, those values are going to a bucket in the array of 0,
Yeah,
1, 2.
the order should be preserved. I think one of the other functions you can call is order by, or blanking on the name of it, but you can sort the data as well.
So we are using a Python, we're using a Spark API in Python, right? with PySpark.
Yes, exactly.
So there's also Scala.
Mhm.
So how is the performance difference between Scala, because it's a native language, and this is PySpark, right? So the speed difference, how does it compare?
So,
Is there any advantage using Scala
can't-
over PySpark?
I don't have a direct answer for you. I think I would be willing to bet that Scala is a little bit faster. The one thing to note is that all of these functions are not being evaluated in Python. So what's going on behind the scenes here is that PySpark is seeing the expression that we're giving it in Python, and behind the scenes it's translating that into Scala.
Okay.
Now that translation is going to add a little bit of overhead, but not as much as if you were just running everything in Python.
Okay. So even if I load a large data set in Scala, and even if I load a large data set in Python, I can do the same thing in PySpark, right?
Yes,
And divide into the clusters and the nodes and
Yep.
everything.
all of this is being, none of this is being actually run in Python itself. There's a Spark server that we're talking to here.
Okay, so the only difference may be the speed is what you're saying.
There might be a slight difference in speed, yes.
Okay.
The other difference, and this is something I've been wrestling with, the Python interface tries to be a little too intuitive, and there's a bunch of things that seem like they should work, but because it can't quite figure out how to translate them into Scala, they don't. But again, I didn't want to give a 1 hour introduction to Scala before doing this. So you may find the Scala interface more predictable and marginally faster, but Python shouldn't be that much worse. Other questions? Okay, so instead of showing it, let's save it for later use. And let's say we want to know how many, where are we? So let's say we want to know how many times a particular word shows up. So we can do that. So right now you have select, that's the select clause of a SQL query. You also get the where clause, although they call it filter. So for example, I could test to see whether the words column is equal to the word tests. Yeah. And again, I get it. Because there's no words column, the word. And again, I get a data frame with the results. Show those results. And I have 2 copies of the word tests, pretty much. 2 copies of the word tests in the entire file. You get aggregates as well. You can do group by. Oops. Group by, so here I'm grouping by the word column, and if I call count, that gives me the count for each word. You can also do and this is where you go back to the documentation and figure out what the right thing to do is. But you can do aggregates. Group by aggregates are a little bit weird because you have to tell it what aggregates you want for each group. But it'll show you the count for each aggregate. Oh, that's how you do it. Okay. So another nice thing that you can do, let's call this word count. So Spark lets you interact with with its data through a variety of different languages. I've been showing you the Python API, but if you're really, really comfortable with SQL, you can do that just as well. So, for example, I have this word count table that has 2 columns, the count and the word. And what I can do is tell Spark I would like to name this particular data frame something. So let's call it word count. So just create or replace temporary view. And now in PySpark, I can tell it, Spark, just run a SQL statement and give me the maximum count from this table, and that'll come back as a data frame. And if I show it, the word that occurs the most times is occurs 47 times. So you can mix SQL, Python, Scala as well. You can interoperate between a couple of different data access languages. Okay, questions so far? All right.
Do you have a really big data set to test this on?
I'm glad you asked. Okay, so so far I've just worked with a text file. I also, the reason that I'm running this on my machine at home is that that machine also is running a Postgres server, which, as it so happens, is receiving a bunch of readings from sensors located around the house. And it's been getting, I believe, one reading every half hour, so there's a fair bit of data here. Give you an idea what this looks like. We've got a couple of different locations of sensors, and essentially all of them look like, so this is Postgres. This is just regular PSQL. Every sensor ID, time, and then data is a JSON object. So Spark gives me the ability to talk to Python. Talk to Postgres. I have to tell it where my Postgres JDBC drivers are. Basically a couple of extra pieces of voodoo. Google it, you'll find this. But essentially, when you run PySpark, you need to tell it where it can find the Postgres drivers. But once you do that, you can start talking to the database. Yes, I know that I am including my a test user password in here. Please don't try and access it in the next half hour. It will be disabled tomorrow. I'm pretty sure you can only access it internally, and I made sure that it has only read access to the two tables we're testing on. But again, please, please don't try hacking my incredibly secure password there. Okay, anyway.
It's like the password an idiot would have on his luggage.
Wait. Remind me to change the password on my luggage. So you basically, so just like before, spark.read, except in this case, we're telling Spark, instead of reading from a text file, read from a JDBC driver. We give it the pretty standard array of JDBC options, the database that we're accessing, the table that we're trying to read from, and then username and password. And then we tell it, go give me a data frame. So it'll sit here for a few moments, load in data, and gives me the one of the tables that I'm interested in. I can do the same thing to get to the other table. And now I have a JDBC connection to the Postgres server running on the same machine. And I have two tables, sensors and readings. And I can access it. I get almost exactly the same interface that I get running this through PSQL. And same thing, sensor ID. Okay, so let's say I want to do a join. I've got two tables here. I've got mapping of sensor IDs to names and sensor IDs to readings. So in order to do this, I have to give the system a few hints here. In particular, since I'm joining two tables, I can no longer refer to just the one table. I can tell Spark to alias the table. So this is kind of like select blah from sensors as S, comma, readings as R, where, and then the join it with readings.r, where r.sensor is equal to s.id. Run that, I get back. So I haven't imported my utility functions yet. Again. Now it has to actually think. So you saw down at the bottom it had a progress bar that becomes even, runs longer. But now I've got the name, the ID. These are going to be the same because that's what the join column was. And then I've got the time in the data before.
So right now, it's still hitting Postgres
Yes.
each time you run it.
I believe it caches the result the first time it gets either table.
Okay, so if you were to run the same question again, you would have the same result, like
Yeah.
instantaneously. But once you store it, then it's in an RDB.
So none of this, RDDs are never stored unless you explicitly write them out to a file, HDFS or anything else.
Okay. So
Spark
it's
may cache them
completely a
internally.
definition, and so it's
Yeah.
always accessing the source data.
Spark will cache things on its own. It is always accessing, you should always assume that it is accessing the source data, but it is somewhat intelligent about it and will cache when it can, when it has enough memory, when it has the resources to do so. Does that answer your
That
question?
does.
I have a question here. Is there a way to just write an SQL statement instead of this converted?
Yeah. So just like before,
Yeah.
you can say spark.sql. So you have to define both of the tables as views first, so that you can access them through Spark SQL. But once you do that, then you can write this as a regular SQL statement. My understanding is that the SQL interpreter is a little bit slow. You don't want to use it for general use, but yes, you could. Does that?
Can I use all the commands of SQL again and here? If I'm using it as a view.
All of the commands of SQL is a very broad statement.
Okay, maybe say the update, insert, select.
No,
because
just select.
Okay.
Okay, so, all right, let's say that I am in particular interested in one of these particular readings. I can, let's see.
I found while I was looking for the question about the help, I found a handy cheat sheet, and I tweeted it out from the Buffalo Data account on Twitter, so if anybody wants to play with this later, that might be really handy.
And I've got, basically all of the code that I'm going through is on GitHub. Again, the password will be disabled by tomorrow.
I was thinking you should have a set of sensors on your garbage can, because this is a really great presentation for just using junk data.
All right, so I'm in particular interested in just to give you a sense of what filtering this data would look like, I'm in particular interested in a sensor that is on our snake tank. And it's ID 4, so I'm just going to use that rather than a join. So, right. So, filter is actually quite convenient because you can write anything. Here I have to be careful. The content of filter, or the one parameter to filter, looks basically just like regular Python. So there's actually a couple of different ways of accessing columns. I'm cheating a little bit. So you'll note that the readings table has a both a time. The readings table has a time field as well as a sensor ID. So I'd like to find the time that is, oops. So I'm going to define a convenience variable that is 4 days ago. And, yeah. So find me all of the readings from 4 days ago where the sensor is the one from the snake tank. And of course that would break.
Do you need to import a time module?
I did. This is complaining about and. Alright. Again, this is how you know that this is live. So there's another way to refer to the columns. If you take the data frame and data frame dot column name is equivalent to column in most cases. Like I said, Python. Oh, of course. That would explain it.
Once you sort of
It wants me to parenthesize properly. There we go. Okay. Now that parenthesized properly, again, this Spark Scala is a little bit more friendly in this respect. It gives you nicer error messages. Right, so we've got a data frame that is all of the snake tank readings from 4 days ago. Let's save that.
well, for more than 4 days ago.
Since 4 days ago.
Okay.
So 4 days ago is a point in time,
Oh, yeah. Okay.
and this is everything that came after that point.
Sorry, I misread the,
So we've got okay. In the interest of time, I'm going to throw in a few very quick pieces of magic. Just to know that this is essentially taking the JSON data and splitting it out. I'm not going to explain this, I'd be happy to do that afterwards. But there is some magic that has to go on in the background in order to pull out the specific fields that I'm interested in. Okay, so now I've got a data frame with the actual temperature of the temperature that's going on in the snake tank. The temperature and the humidity. And what I would like to do is, let's just get the temperature by time. So this is grabbing the data field, grabbing the temperature component of it, since this is a JSON object, and then it's calling it temperature, and otherwise this is basically just a regular select statement. So what we have here is the temperature by time. Now, this is where I cross my fingers and hope that this works properly. All right, so who here is familiar with pandas? Who here has heard of pandas? Okay, so pandas is the other, apart from Spark, the other kind of major data munging tool that uses Python. And fortunately, Python and pandas are kind of designed to interoperate. So now that I've run my query, I have a data frame. I can take this data frame and convert it to pandas. And now I have a pandas data frame. Why is that cool? That is cool because now I can do something like this. Doing this properly.
I think you need the matplotlib.pyplot.
Pyplot. I did have it written down. So, there we go. So now, in principle, I can just plot the So this would have been really cool if it just, oh, no. Oh, there we go. So yeah, then you can take your data out of matplotlib, throw it into pandas, and start plotting.
So when you converted your data frame into a pandas object, you still get the same faster speed?
No. So at that point, when you convert it to pandas, it runs the query, downloads it, and then you're in pandas land.
Okay, so everything from Spark itself is all data entry.
Yeah. Exactly. But then, if you want, you can then take your pandas data object and put it back into Spark. Of course, then you're now at that point you're talking in Python land, and you get the speed penalties of dealing with Python. But by the point you're talking about graphing your data, you presumably have reduced it to the point where it's manageable.
Got it.
Okay, so I mean, there's a bunch of I could do a little bit more here, but I want to have time for the last thing. Let me see if I... Is it still alive? Yes, it is. The cool thing about Spark isn't that it lets you run things on your own computer. The cool thing is that it lets you run queries on large clusters. So most of the major providers have something that lets you just deploy Spark clusters for free. Google in particular has this thing called Dataproc. It's the one I decided to pick up and basically say, give me a cluster. And I don't want to be going in South America. America seems good. Give me a couple of CPUs. The free tier will only give you 8 CPUs total. So we'll do 3 worker nodes, 1 master node with 2 CPUs apiece. Everything runs smoothly here. Okay, so the Google Cloud Platform gives you a handy little console, which is, assuming this doesn't break, this should be basically just regular Unix. It has the standard stuff that you'd expect a Unix platform to have, like, for example, Emacs. And you'll note this is also running in a web browser. Kind of cool. I've got, so this is connecting also to my home server, but because Google is not running on the same machine as my Postgres server, I have a JSON REST endpoint that lets me get the temperature in my house. What you have here is essentially a Python script that reads in data from my home server, initializes Python, so this is essentially what PySpark will give you for free, and then creates a data frame from the data that it loaded earlier, and then pulls out the average temperature, computes the average temperature and number of records that it pulled off of the endpoint. Nothing fancy, but just to give you a taste of what this looks like, this is just a regular Python script with relevant boilerplate added. Okay, so there is a magic incantation, which we'll tease apart. Google gives you a tool called gcloud, which does have a handy help tool. In particular, if you look, it has a bunch of operations or a bunch of groups, one of which is Dataproc. Gcloud Dataproc. Call that. It helpfully tells you that you have a couple of different things that you can do to manage your Dataproc clusters. In this case, we are interested in jobs. And you can basically go through a similar process of build the command up as you, it's a well-documented system, essentially. Every command will tell you what options you have for the next step in the process. But just to run over this, you are talking to Dataproc specifically. You want to deal with a Dataproc job. You would specifically like to submit a job to run. The language is PySpark, and the name of the PySpark script. And then this cluster here is whatever your cluster name is, in this case, cluster EC36. And so this will basically tell the Google Cloud to start running temperature.py. This will probably take a little bit since it's really geared for large workloads. And since the cluster is still being provisioned, so this might take a few seconds, but it'll eventually start running. It'll start talking to the Google Cloud, submit the application to run, and in a few seconds we'll see a response. So progress bar, and there you go. So it pulled everything from server home. It computed the average temperature, the count, and then some final status. Yeah.
So when you did this, is it talking to your the database at your house or?
Kind of. It's talking to the database just in a different way. It's using a REST endpoint rather than Python.
So the cluster is talking to your database?
Yeah. I have an API that lets me query the several specific sensors from home. So it's here. You want to see what that looks like? It is just talking to a URL that's returning a bunch of JSON. Talking to the URL, returning a bunch of JSON, picking out a specific field from the JSON, and then building a Spark data frame out of that JSON. If the data was already slightly more nicely formatted, I could just get Spark to get the data directly, rather than first loading it in through Python and then passing the data to Spark that way. Again, I was kind of lazy here, so I did the data processing in Python and then a couple of basic transformations in Python, and then pass that to Spark. Okay, well, that's about the lot of it. Final questions?
Okay, so you're on the Google Cloud. Is there a Docker? Is there, I saw you, one of the things that came up when you did an LS is Kubernetes. So you're doing some kind of orchestration with containers somewhere.
I believe it uses Yarn.
Okay.
That's weird. Burned in the screen. So I believe it uses, G-Cloud uses Yarn in the background. That is a different talk that I am not prepared for. But
Just complicated enough.
So there was a question asked earlier about support of Spark SQL for all, obviously not insert update, but I think it was your question. I want to say maybe it was on the lines of, can you do group by and having clauses?
Yeah,
And
so-
joins and all that stuff.
So having would just be, you first do a group by, then the aggregate, and then do a filter on the result. I did go through grouping, well, my laptop's now off, but so yeah, you can do group by, you tell it which columns you want to group by, and then tell it what aggregates you want to run. Essentially, anything that you could do in SQL, there is a function that you can do to apply the same
Do
transformation.
you do common table expressions and is it really far out?
So a common table expression is you save your you save your data frame as a variable, and then you can reuse the variable multiple times in the expression. It is basically SQL, but designed around, or designed more from a Python or Scala or.
Okay, so it's more, what you're describing sounds more like it's Pythonic.
Yeah, it's more Pythonic.
Okay.
The functionality of SQL is there. It is essentially just expressed. Every clause is expressed as another function that you add on to the chain of functions that you use to build up the final result data frame. And again, you're not modifying anything. You're just producing. You're transforming the data the same way you would with a SQL expression. So yeah, views. They're views. Everything's a view.
Actually, in a multi-node scenario, like when you talk about MapReduce, so there are like multiple mappers distributed and then multiple reducers and then.
Yeah. So in the cloud setting here, this is. I have no way of proving this to you, but it is running on 6 separate. Three computers, 3 virtual computers with 2 cores apiece.
So, what's the major difference when it comes to Hadoop and Spark? Because you said that like Spark is faster, but in terms of functionality, like because I think Spark also uses the MapReduce thing. So where does it, where does that difference come from?
So the main difference is, there are 2 main differences. So first off, Spark is aware of individual rows and doesn't try and, the scheduler is is more flexible. So with MapReduce, there's a hard barrier in between stages. If you can't start the reduce until the map is finished. They've changed that a little bit, so that may not be entirely correct, but that's one thing. The second thing is that Spark, and specifically Spark data frames, are aware of the schema of the data. They're aware of the structure of the data, and I'm not entirely sure whether they use database statistics, but when you build up a view, it won't naively just try and execute every stage in the pipeline. It will first throw a query optimizer at the expression that you've given it, and the resulting query is going to be a lot more efficient. And that's something that MapReduce can't do, or that you can't do with MapReduce, because Hadoop doesn't know what is going on in the mapper. It doesn't know what's going on in the reducer. Is that? There's been some talk of wanting to actually have Spark push operations down into lower tiers as well. So when you tell it, access the contents of this table from a database, it doesn't actually try and do things like pushing joins or filters down into the underlying database. There's plenty more room for optimization here, but at least the basics of query optimization that we've picked up over the past 4 decades are there, which is not there in MapReduce.
Okay.
So you said this cluster has about 3 computers in the background?
Yeah, I mean, you can provision it with whatever you like.
Whatever number. When you run that picture.py, so there was a link to that URL, right? When you execute that code, all the 3 machines talk to your.
Okay, so let's go through this.
So what does
So what is happening here? So this is all regular Python. This is all regular Python. So this is the master. The cluster that I created has one worker node with one master node with 2 cores and one set of three worker nodes each with 2 cores. So this is the master node talking to the server to download the data, pulling out the relevant field. Now here's where Spark kicks in. So this is the code that tells Python to connect to the Spark server, or the Spark cluster, and start doing things. This is the line. This line is basically it saying, okay, I have a bunch of data in Python land. Make it parallelize it, make it Spark-esque. And now this df, this is me talking to Spark. So this operation is entirely in Spark. And then show is basically coming back to Python, the response is coming back to Python.
So clearly this is a tool that's aimed at like large data sets so you can distribute the work over lots of nodes. But under the hood you're using some tools that you might already be familiar with, or you could use standalone, like you could use a SQL server and pull data into pandas, data frames, just using those tools by themselves. So what's the breaking point, or the breakoff point where you go and start doing this and put Spark into the picture? Because it doesn't sound like you'd want to have it for a small data set other than as a maybe academic exercise.
So the interface is very pandas-esque. If you're familiar with pandas, you will probably find a lot of not just the commands themselves, but the quirks of Python talking to Spark to be very similar to the quirks you'd experience in pandas. The breaking point.
What I mean is the point where you decide, okay, I need to be in Spark because I have this much data or that much data, or
When is your machine slow enough? When does your machine slow down? If you have a machine that is capable of processing a gigabyte of data in pandas, great. You know,
so really
keep doing it.
there isn't really a need to go into this unless you have some fairly ambitious.
If you have resiliency concerns as well, so if you're using this data to feed something else that needs to be on all the time, then you have a cluster that can handle fault tolerance.
Well, you could have that with a database service too, right? You could have
A single node of running Python. Basically, if a single node running Python will do what you need it to do, then this is way overkill.
Okay. Yeah, that's what I guess what I'm getting at, is like, or, you know, when are you just doing something as overkill versus
So there's,
doing a need for it?
there are a few advantages to this. So first off, it will natively talk to, so Spark will natively talk to a pretty wide variety of different data sources. I know pandas will already do some of this, but if you want to talk to JDBC, if you want to talk to HDFS, if you want to talk to regular data files, you're fine with pandas. But there's a much wider range of adapters, I suspect, for Spark than there is for pandas. So being able to interface.
So convenience.
Yeah, there's some convenience factors. Again, performance, I mean, if it takes you an hour on a single node and you happen to have a cluster just lying around, or money to pay Google for their cluster, you can cut that down by a bunch. I mean, there's a lower bound. If you're running in under a minute, then Spark is probably going to be slower because dealing with a cluster gives you, there is some overhead.
But I guess if you had a terabyte, say, of data, Spark's probably a pretty good choice then to look at.
I can't give you a fixed trade-off. It's also a matter of computation, not just data size, but if it takes you an hour to process your data, if I'm just looking for instances of a particular word, I mean, grepl chow through a terabyte of data in a few minutes, if even. It is another tool for your toolbox.
It's always the aesthetics or depends.
Yeah, that's my favorite answer to,
Yeah, I know that there's no like set, limit or a threshold, it's like automatically kicks in, but I was curious when companies or projects would typically help, so I guess it's, your mileage will vary.
Spark is also going to be more expensive. So Pandas is going to be faster if you're running it on a single node. Spark running on a single node, you might be able to take advantage of multiple cores if you have an 8-core machine or something like that. Spark might be faster, but
So it's more thirsty for resources.
I mean, if you really want to take advantage of Spark, you want a full cluster, and
Yes.
if you don't happen to have a cluster lying around, then you have to pay for one.
Do you have to invest, let's say you do MongoDB, that, the thing about Mongo is that you have to have, you do sharding, and you try to achieve the scalability, you have to have additional configuration machines and machines that act as replicas that failover nodes within each shard, and it gets really expensive to have all these machines. Is it that? Does each machine in a Spark cluster actually do work? Or
So a Spark cluster is comparable to a Hadoop cluster. In fact, most of the default use case for Spark is that you talk to HDFS to get your data. Spark was kind of designed to work, to kind of seamlessly integrate into existing Hadoop deployments.
I'm not familiar with Hadoop, but I guess my question is it when you make that investment in a cluster with Spark, is every node that you're doing?
So there's
doing work, or is it just sitting there being like a?
there's a master, there's so there's a master, there's workers, and there's data nodes. It is typical for the data nodes and the workers to be the same.
So you're pretty much you're really using the machines to do stuff and not having them be for failover.
Well, that's the thing. So with Mongo, people are talking to it, people are interacting with it constantly, and you need redundancy on individual data records because people are always interacting with those records. With Hadoop or with Spark that are more OLAP-centered, if a worker fails, you haven't lost anything. You've lost time, but you can always restart the worker from you can restart another worker from where the original one left off. So there's not really a difference between, the workers are a lot more interchangeable.
And you have to restart that, or does
The system does. If anything breaks, you fail over.
self-healing?
Yeah. Well, okay. Here I'm a little bit out of my league. I don't know how. I believe it's just the case that as worker nodes come up, they connect to the master, and then once they're connected to the master can start assigning them tasks. Same thing for the data nodes. Self-healing implies that the system can also kind of talk to, can bring nodes up and down, which
Yeah.
I don't believe is the case.
Okay.
But
It knows when stuff is up or down, and not overloaded, not to send.
I believe so, yeah. You need some other orchestration service on top of it to manage which nodes are running.